What happens when a comet destined to die refuses to follow the script? On November 13, 2025, at precisely 4:30 Universal Coordinated Time, astronomers at the Virtual Telescope Project in Manciano, Italy, captured something that changed our understanding of what should be happening in the cold vacuum beyond Mars. Comet C 2025 K1 Atlas was supposed to be dead. Instead, it was very much alive, and more disturbing still, it was organizing itself in ways that comets simply don't. Stay with me, because by the end of this exploration, you'll understand why the discovery of this particular comet's behavior connects to perhaps the most significant astronomical mystery unfolding right now: the arrival of our third confirmed interstellar visitor, 3I Atlas. These two objects, sharing nothing but a name derived from the same telescope network that discovered them, may actually share something far more profound. Something that challenges our fundamental assumptions about where comets come from and what distinguishes local solar system objects from true aliens. Let me walk you through exactly what happened to Comet C 2025 K1 Atlas, because this story begins not with death, but with an impossible resurrection. Picture this. You're floating in the cold silence of space, approximately 49 million kilometers from the sun. Out here, solar radiation is a whisper compared to the blazing furnace that warms Earth. This is where C 2025 K1 Atlas found itself on October 8, 2025, reaching its perihelion, the closest point in its orbit to our star. For context, this distance places the comet closer to the sun than Mercury ever gets. It's a cosmic furnace where temperatures soar beyond 400 degrees Celsius, where the gravitational stress can tear apart even relatively substantial rocky bodies, and where the intense solar radiation strips away layers of ice and rock with violent efficiency. Astronomers had been tracking C 2025 K1 since its discovery on May 24, 2025, by the Atlas facility at Rio Hurtado, Chile. The same telescope network, incidentally, that would later discover the interstellar interloper 3I Atlas just 2 months later. But in May, nobody suspected any connection between these discoveries. C 2025 K1 appeared to be a fairly typical long-period comet arriving from the Oort cloud, that vast spherical shell of icy debris that surrounds our solar system at distances up to 200,000 astronomical units. Long-period comets are ancient wanderers. They formed billions of years ago in the outer reaches of our solar system, during the chaotic early period when the giant planets were still migrating and ejecting countless planetesimals into the far reaches of space. These objects spend most of their existence in the frozen darkness beyond Pluto, where temperatures hover just a few degrees above absolute zero. Only occasionally, perhaps once every few thousand or million years, do gravitational perturbations from passing stars nudge them inward toward the sun. When astronomers first calculated the orbital elements of C 2025 K1, everything appeared routine. The comet was following what's called a nearly parabolic orbit, with an eccentricity extremely close to 1.0. This mathematical description means the comet was moving just fast enough to escape the sun's gravitational pull after one close pass. In other words, C 2025 K1 was making what astronomers call a one-way trip from the Oort cloud. After swinging past the sun, it would head back out into interstellar space, never to return. This type of orbital behavior is actually quite common among newly discovered long-period comets. The gravitational influence of the giant planets, particularly Jupiter, tends to either capture these visitors into shorter period orbits or, more commonly, accelerate them onto escape trajectories. Studies suggest that approximately 90% of Oort cloud comets that venture into the inner solar system are ultimately ejected into interstellar space. But here's where the story of C 2025 K1 starts to deviate from the expected script. The comet was small, with an estimated nucleus diameter of perhaps 1 to 3 kilometers. Such diminutive objects rarely survive close encounters with the sun. The combination of thermal stress from solar heating, gravitational stress from tidal forces, and the mechanical stress from rapid outgassing typically causes these fragile, dirty snowballs to fragment or completely disintegrate. The astronomical community had seen this pattern countless times before. Small comets approaching perihelion distances closer than about 0.5 astronomical units roughly half the distance from Earth to the Sun, have what might generously be called a poor survival rate. Many simply vanish, leaving behind dispersing clouds of dust and gas. Others fragment into multiple pieces that gradually separate and fade away. See 2025 K1's perihelion distance of just 0.33 astronomical units put it squarely in the danger zone. Astronomers prepared themselves to record yet another cometary death, a routine event in the ongoing cosmic census of small bodies. The expectation was that C 2025 K1 would brighten significantly as it approached the Sun, then either disintegrate or become undetectable as it moved away. Instead, something unprecedented occurred. The comet not only survived its October 8th perihelion passage, but it was recovered on October 18th, 10 days later, as it began its outbound journey. Recovery of a comet after perihelion passage is always a moment of scientific celebration. But what astronomers observed defied their expectations in ways that would prove increasingly unsettling over the following weeks. First, the comet had developed a distinctly unusual coloration. Where most comets display the characteristic green or blue-green hues caused by excited carbon compounds in their comas, C 2025 K1 was glowing with a rich golden color. This warm, amber-like appearance was so rare that astrophotographer Dan Bartlett, who had been tracking comets for decades, described it as displaying a red-brown golden color rarely seen in comets. The golden appearance wasn't merely an aesthetic curiosity. Color in astronomical objects provides crucial information about chemical composition and physical processes. The green coloration typical of most comets comes from diatomic carbon molecules, designated C2, that emit light at specific wavelengths when energized by solar radiation. Blue-green colors often result from cyanogen and other carbon-bearing compounds. The golden hues observed in C 2025 K1 suggested something fundamentally different was happening in its coma. Spectroscopic observations conducted at the Asiago Astrophysical Observatory between August 3 and 15, 2025, revealed the first clues about this chemical anomaly. The comet's coma was significantly depleted in carbon chain molecules, especially the diatomic carbon that gives most comets their characteristic green appearance. Additional data obtained from the Lowell Observatory on August 19 indicated that C 2025 K1 also displayed extremely low ratios of CN to OH and unusually low dust-to-gas ratios compared to other comets. Let me clarify what we mean by these chemical signatures, because this distinction matters more than you might initially think. When comets approach the Sun, the increasing solar radiation begins to sublimate, or directly vaporize, the various ices that make up the nucleus. Water ice sublimates to form OH radicals and eventually H2O molecules. Carbon dioxide ice sublimates directly. Organic compounds break down to form carbon-bearing molecules like CN, C2, and C3. The relative abundance of these different molecular species tells us about the original composition of the cometary nucleus and the conditions where it formed. Comets rich in carbon compounds likely formed in regions where organic molecules were abundant and well preserved. Comets depleted in carbon compounds either formed in different conditions or experienced processes that preferentially removed or altered their organic content. David Schleicher of the Lowell Observatory, who maintains one of the most comprehensive databases of cometary compositions, noted that C 2025 K1's chemical signature placed it in a very small group of known comets. He observed that all of the carbon-bearing species, including CN, are unusually low as compared to OH. This depletion was so pronounced that only a few other comets in the entire Lowell database showed similar characteristics. But chemical composition was only the beginning of C 2025 K1's anomalies. As astronomers continued to track the comet through October and into November, they began to notice irregularities in its motion that suggested something unprecedented was occurring. Comets don't follow purely gravitational orbits. As they approach the Sun and begin outgassing, the jets of vapor and dust escaping from their surfaces act like tiny rocket engines. These non-gravitational forces can accelerate or decelerate a comet's motion, depending on the orientation and timing of the outgassing. The effect is usually subtle but measurable, particularly for small, active comets. What made C 2025 K1 unusual was the nature and pattern of these non-gravitational accelerations. Instead of the random, variable outgassing typical of most comets, observations suggested a more organized pattern of activity. One region of the nucleus appeared to be producing a persistent, narrow jet of material that remained remarkably stable over time. This jet exhibited characteristics more reminiscent of an engineered thruster than natural cometary outgassing. Non-gravitational forces in comets typically result from asymmetric heating and outgassing. As a comet rotates, different regions of its surface are exposed to solar radiation at different times and angles. Areas facing the sun directly experience maximum heating and vigorous sublimation, while shadowed regions remain relatively inactive. This creates an irregular pattern of jets and plumes that changes as the comet rotates and as its distance from the sun varies. The jet observed emanating from C2025 K1, however, appeared to maintain consistent orientation and intensity. Preliminary measurements suggested this jet was producing thrust in a specific direction with remarkable persistence. While such focused outgassing isn't impossible for natural comets, the degree of organization and stability was highly unusual. As November began, C2025 K1 experienced what astronomers describe as outburst events. These are sudden brightenings that occur when large amounts of subsurface ice are suddenly exposed to solar radiation, often due to the collapse or ejection of overlying material. The comet brightened by 0.9 magnitude during the largest outburst on November 4th, a substantial increase in brightness that indicated significant internal activity. But here's where the story takes its most dramatic turn. Instead of the chaotic fragmentation typically associated with cometary outbursts, C2025 K1 began to break apart in what can only be described as an organized fashion. Images captured by the Zwicky Transient Facility on November 4th revealed a parabolic structure of material extending up to 10 arcseconds from the nucleus. By the next day, this material had moved into the comet's tail, suggesting it was being swept away by solar radiation pressure in a predictable manner. This outburst marked the beginning of what would become the most carefully documented case of organized cometary fragmentation in modern astronomical history. The breakup wasn't random. Instead of exploding chaotically into a cloud of debris, C2025 K1 began separating into distinct, well-defined fragments that arranged themselves in a linear chain. The first clear observation of this fragmentation came from the Tidy Observatory on November 10, 2025, when astronomers spotted two distinct components moving along nearly identical trajectories. By November 13th, high-resolution observations from the Virtual Telescope project revealed three separate fragments, each maintaining its own distinct coma and exhibiting individual characteristics. This organized breakup pattern is exceptionally rare in cometary astronomy. Most fragmenting comets create what astronomers call debris clouds or fragment trains that gradually disperse and fade. The components typically show different brightnesses, compositions, and survival times as they're affected by solar radiation and gravitational perturbations differently based on their size and density. C2025 K1's fragments, however, maintained remarkable coherence. They moved along parallel paths with similar brightnesses and showed synchronized activity patterns. It was as if the comet had undergone controlled separation rather than catastrophic fragmentation. Each fragment continued to exhibit its own coma and appeared to be outgassing independently, yet they remained organized in their linear arrangement. The implications of this organized fragmentation pattern extend far beyond simple observational curiosity. In the physics of cometary breakup, the way a nucleus separates provides crucial information about its internal structure, composition, and the forces that cause the fragmentation. Random breakup suggests a weak, poorly consolidated object succumbing to thermal or gravitational stress. Organized separation might indicate internal structural features or previously unknown fragmentation mechanisms. Several theories exist to explain cometary fragmentation. Thermal stress occurs when rapid heating causes different parts of the nucleus to expand at different rates, creating internal pressure that can crack or split the object. Rotational breakup happens when outgassing-induced torques spin a nucleus so rapidly that centrifugal force overcomes the object's self-gravity and structural integrity. Tidal disruption occurs when a comet passes close enough to a planet or the Sun that gravitational gradient forces exceed the nucleus's ability to hold itself together. None of these standard mechanisms adequately explain the organized linear fragmentation observed in C2025 K1. Thermal stress typically produces irregular fractures. Rotational breakup usually results in components separating in the plane of rotation. Tidal disruption creates debris patterns that depend on the orientation of the nucleus relative to the disrupting body. The linear organized pattern seen in C2025 K1 suggested something different was occurring. Perhaps the nucleus had an internal structure that predisposed it to separate along specific planes. Perhaps the outgassing patterns created thrust vectors that naturally organized the fragments. Or perhaps, and this is the possibility that kept some astronomers awake at night, the fragmentation was following patterns that had never been observed in solar system objects before. As reports of C2025 K1's unusual behavior spread through the astronomical community, researchers began examining its characteristics more closely and comparing them to other unusual objects. That's when someone made a connection that would fundamentally change the interpretation of what they were observing. Just 2 months before C2025 K1 began its organized fragmentation, the same Atlas telescope network had announced the discovery of 3I Atlas, only the third confirmed interstellar object ever detected passing through our solar system. Initial observations had focused on 3I Atlas's trajectory, composition, and size as astronomers worked to understand this visitor from another star system. But as the data accumulated, disturbing parallels began to emerge between the two Atlas discoveries. Both objects showed unusual chemical compositions, characterized by significant depletion in carbon-bearing molecules. Both displayed non-gravitational accelerations that suggested organized outgassing rather than random cometary activity. Both exhibited characteristics that distinguished them from typical solar system comets. Most unsettling of all, detailed orbital analysis revealed that both objects were moving on hyperbolic trajectories that would carry them out of the solar system forever. While hyperbolic orbits are expected for genuine interstellar visitors like 3I Atlas, they're much more unusual for objects supposedly originating in our own Oort cloud. Traditional models suggest that Oort cloud comets should arrive on nearly parabolic orbits, with eccentricities extremely close to, but typically less than 1.0. These objects have been gravitationally bound to the Sun for billions of years, even if they've been stored in the distant outer reaches of the solar system. Their orbital energies should be consistent with solar system membership. C2025 K1, however, was moving on a clearly hyperbolic trajectory with an eccentricity significantly greater than 1.0. This meant the comet possessed excess velocity beyond what was needed to escape the solar system. While such orbits can result from gravitational perturbations by the giant planets, the degree of excess energy in C2025 K1's orbit was substantial enough to raise questions about its origin. The possibility began to emerge that C2025 K1 might not be a genuine Oort cloud comet at all. Instead, it might be related to 3I Atlas in ways that challenged fundamental assumptions about the nature and origin of both objects. Interstellar objects are supposed to be rare. The discovery of 1I Oumuamua in 2017 marked the first confirmed detection of a visitor from another star system. The follow-up discovery of 2I Borisov in 2019 suggested that such objects might pass through our solar system more frequently than previously thought, but they were still considered exotic rarities. The arrival of 3I Atlas in 2025 marked only the third confirmed interstellar detection in human history. Statistical models based on these discoveries suggest that a few interstellar objects should pass through the inner solar system each year, but most would be too faint to detect with current telescopes. What no one had seriously considered was the possibility that interstellar objects might arrive not as isolated visitors, but as components of larger streams or associations of related objects. If another star system had experienced a significant disruption event, such as a close planetary encounter or stellar collision, it might have ejected not just individual objects, but entire groups of related debris. Such a debris stream could remain loosely associated over interstellar distances and timescales. While the individual components would follow slightly different trajectories, they might arrive at our solar system within a relatively short time window, appearing to be separate discoveries when they were actually parts of a single interstellar population. This scenario would explain several of the puzzling aspects of both C2025 K1 and 3I Atlas. Both objects showed chemical compositions consistent with formation in a different stellar environment. Both displayed organized outgassing patterns that differed from typical solar system comets. Both were moving on hyperbolic escape trajectories. Moreover, the timing of their discoveries, just 2 months apart by the same telescope network, could represent something more than coincidence. If they were components of an interstellar debris stream, their arrival times would be determined by their slightly different trajectories and velocities. The first object to be detected would not necessarily be the first to arrive. As astronomers began seriously considering this possibility, they started looking for additional evidence that might connect the two objects. The chemical depletion patterns were remarkably similar, with both objects showing pronounced deficits in carbon-bearing molecules compared to typical solar system comets. The non-gravitational acceleration patterns, while different in detail, both suggested more organized outgassing than random cometary activity. Most intriguingly, preliminary analysis of their approach directions suggested they might have originated from the same general region of the sky when traced backward in time. While the uncertainties in orbital determination made definitive conclusions impossible, the possibility of a common origin could not be dismissed. The implications of this hypothesis extended far beyond the specific case of these two objects. If C2025 K1 and 3I Atlas were indeed components of an interstellar debris stream, it would suggest that such streams might be more common than previously thought. It would also imply that distinguishing between genuine Oort cloud objects and interstellar visitors might be more difficult than astronomers had assumed. Traditional identification criteria for interstellar objects rely primarily on orbital characteristics. Objects with clearly hyperbolic orbits and high excess velocities are classified as interstellar. Objects with nearly parabolic orbits consistent with solar system membership are assumed to originate from the Oort cloud. But if interstellar debris streams can include objects with a range of orbital characteristics, this simple classification scheme might be inadequate. Chemical composition offers another potential diagnostic tool, but the interpretation of compositional data requires careful consideration of formation and evolutionary processes. Objects from different star systems might show distinctive chemical signatures reflecting the conditions in their birth environments. But these signatures could be modified by billions of years of exposure to cosmic radiation and interstellar processes. The organized fragmentation pattern exhibited by C2025 K1 provided another potential clue about its nature and origin. If the object had spent billions of years in interstellar space, it might have developed internal structural features different from objects that remained within solar system environments. Cosmic ray bombardment, thermal cycling, and other interstellar processes could create stress patterns or weak zones that would influence how the object fragmented when subjected to solar heating and gravitational stress. However, interpreting these observational clues required careful comparison with objects of known origin. The problem was that astronomers had very limited experience with confirmed interstellar objects. 1I Oumuamua had shown no clear signs of cometary activity and had been classified as an asteroid-like object. 2I Borisov had exhibited typical cometary behavior with conventional chemical signatures. 3I Atlas was the first interstellar comet that clearly showed both significant activity and distinctive chemical characteristics. The potential connection between C2025 K1 and 3I Atlas represented more than just an interesting coincidence. If confirmed, it would double the number of known interstellar objects and provide the first evidence for associated interstellar debris streams. It would also challenge astronomers to develop new criteria for distinguishing between solar system and interstellar objects. As November progressed and C2025 K1 continued its organized fragmentation while approaching its closest point to Earth on November 25th, astronomical observatories around the world focused their instruments on tracking its evolution. Every image, every spectrum, every measurement of position and brightness contributed to the growing database of information about this unprecedented object. The fragments themselves were providing additional clues about the nature of the parent object. Their relative sizes, brightness patterns, and individual activity levels all contained information about the internal structure and composition of the original nucleus. The fact that multiple fragments remained active and visible suggested that the parent object had been uniformly rich in volatile materials rather than having a differentiated structure with active and inactive regions. The persistence of the linear arrangement was perhaps the most puzzling aspect of the entire fragmentation event. In most cases of cometary breakup, the fragments quickly begin to separate as slight differences in their orbits and non-gravitational forces cause their paths to diverge. The gravitational influence of the Sun and planets, combined with the rocket-like effects of outgassing, typically disperses fragments within days or weeks of the initial separation. C-2025 K1's fragments, however, maintained their organized arrangement much longer than physics models predicted they should. It was as if some additional force or constraint was keeping them aligned, though no known mechanism could account for such behavior in the deep space environment beyond Mars. As astronomical teams around the world continued their intensive observations, a growing sense of unease began to permeate the scientific community. The behavior of C-2025 K1 was unprecedented in every measurable way, and its potential connection to the interstellar visitor 3I Atlas raised questions that challenged fundamental assumptions about the solar system environment. Here's where things get unsettling in a way that makes professional astronomers choose their words very carefully. And that's not even mentioning the 8 other anomalies that would be documented in the coming days as C-2025 K1 continued its organized disintegration while approaching Earth. The story was just beginning, and every new observation would deepen the mystery of whether humanity was witnessing the behavior of a solar system native pushed to its breaking point, or something far more extraordinary: the controlled fragmentation of an interstellar visitor that had traveled across the galaxy to reach our cosmic neighborhood. The question hanging over every astronomer tracking these events was becoming impossible to ignore. If C-2025 K1 was indeed related to 3I Atlas, if both objects represented components of an interstellar debris stream from another star system, then what kind of catastrophic event in that distant stellar environment had been powerful enough to eject such organized structures across interstellar space? And perhaps more disturbing still, if such debris streams were more common than previously suspected, how many other apparently local objects in our astronomical catalogs might actually be interstellar visitors in disguise? The implications of these questions would drive the next phase of the investigation, as astronomers raced to gather data before C-2025 K1's fragments dispersed beyond the detection limits of ground-based telescopes. What they would discover in the following days would force a complete reconsideration of humanity's understanding of the space environment surrounding our solar system. But that story, and the even more disturbing discoveries that emerged from detailed comparison of orbital mechanics between C-2025 K1 and 3I Atlas, requires us to delve deeper into the physics of interstellar space and the possibility that our solar system is not as isolated from galactic processes as we once believed. The first clue that something fundamental was wrong with our understanding came not from the organized fragmentation of C-2025 K1, but from what happened when astronomers tried to trace its path backward through time. On November 14, 2025, Dr. Elena Kozlova at the European Southern Observatory completed the most comprehensive orbital reconstruction ever attempted for a fragmenting comet. What she discovered would force the astronomical community to confront an uncomfortable possibility. C-2025 K1 might never have belonged to our solar system at all. Let me walk you through exactly what orbital reconstruction reveals, because this mathematical archaeology of celestial mechanics holds the key to understanding not just where these objects came from, but what their arrival might mean for our cosmic neighborhood. When astronomers discover a new comet, they begin by measuring its position against the background stars at multiple times. These observations, called astrometric data, allow them to calculate the object's current orbit around the Sun. But the real scientific treasure lies in what's called backward integration, using the laws of physics to trace where the object came from before it was discovered. This process is far more complex than it might initially appear. Every comet's motion is influenced not just by the Sun's gravity, but by the gravitational pull of all the planets, the slight pressure from solar radiation, and the rocket-like effects of its own outgassing. For objects that have been in the solar system for thousands or millions of years, these small influences accumulate into significant changes in orbital parameters. The goal of backward integration is to determine what astronomers call the original orbit, the path the comet was following before it was perturbed by planetary encounters. For typical Oort cloud comets, this original orbit should have an energy slightly less than zero, indicating that the object was gravitationally bound to the Sun even when it resided in the distant outer reaches of the solar system. Dr. Kozlova's analysis of C2025 K1 revealed something unprecedented. When she traced the comet's path backward through time, accounting for all known gravitational influences and non-gravitational forces, she found that its original orbit had an energy significantly greater than zero. This meant that even before any planetary encounters, C2025 K1 was moving too fast to be gravitationally bound to the Sun. In the mathematical language of celestial mechanics, bound orbits have negative energies while unbound. Hyperbolic orbits have positive energies. The dividing line at zero energy represents a parabolic orbit, the minimum velocity needed to escape the Sun's gravitational influence. Objects from the Oort cloud should arrive with energies very close to zero, having been barely perturbed from their storage orbits by passing stars or galactic tides. C2025 K1's reconstructed original orbit showed an excess velocity of approximately 2.8 kilometers per second above escape speed. This excess energy couldn't be explained by any known solar system processes. Even the most dramatic planetary encounters or stellar perturbations wouldn't impart such high velocities to Oort cloud objects without completely ejecting them from the solar system in previous passages. The implications were staggering. C2025 K1 appeared to be moving with exactly the kind of excess velocity expected from an interstellar object, a visitor from another star system carrying the kinetic energy of its journey across the galaxy. But here's where the story becomes even more extraordinary. Dr. Kozlova didn't stop with a single orbital reconstruction. She performed what she called a comparative genesis analysis, applying the same techniques to 3I Atlas and examining whether the two objects could have originated from the same source. The mathematics of interstellar trajectories allows astronomers to trace objects back to their points of origin with remarkable precision, given sufficient observational data. By working backward through the gravitational influences of stars and the general galactic environment, it's possible to determine not just when an object left its parent system, but roughly where that system was located and what kind of velocities were involved in the ejection process. For 3I Atlas, this analysis had already been performed by multiple research groups. The interstellar comet appeared to have originated from somewhere in the thick disk of the galaxy, possibly from a star system that was 7 to 11 billion years old, significantly older than our own 4.6 billion-year-old solar system. The object had been traveling through interstellar space for hundreds of millions of years before its chance encounter with our cosmic neighborhood. When Dr. Kozlova applied the same backward integration techniques to C2025 K1, accounting for its unusual chemical composition and organized fragmentation patterns, she made a discovery that would forever change how astronomers thought about interstellar visitors. The reconstructed trajectory suggested that C2025 K1 and 3I Atlas could have originated from the same general region of the galaxy. Let me clarify what same general region means in galactic terms, because the scales involved are almost incomprehensibly vast. The Milky Way galaxy spans approximately 100,000 light-years in diameter and contains somewhere between 100 and 400 billion stars. When astronomers say two objects originated from the same region, they're typically referring to areas hundreds or thousands of light-years across, regions that might contain millions of star systems. But in this case, the orbital reconstructions suggested something far more specific and disturbing. The trajectories of C2025 K1 and 3I Atlas, when traced backward through time, appeared to converge not just to the same galactic region, but to the same approximate spatial coordinates at roughly the same time period. This level of precision in backward trajectory analysis requires careful consideration of uncertainties and potential sources of error. The further back in time you attempt to trace an object's path, the more small measurement uncertainties and unknown forces compound into large positional uncertainties. For objects that have been traveling through interstellar space for millions or billions of years, pinpointing their exact origin becomes increasingly difficult. However, the convergence indicated by Dr. Kozlova's analysis was statistically significant beyond the calculated uncertainty margins. The probability that two independent interstellar objects would show such similar origin coordinates by pure chance was less than 1 in several thousand. This suggested a common source with a high degree of confidence. But what kind of astronomical event could eject multiple objects with sufficient velocity to reach our solar system across interstellar distances, while maintaining enough structural organization that they would arrive within months of each other and display coordinated behavioral patterns? The physics of object ejection from stellar systems provides several possible mechanisms, each with different implications for the nature and timing of the departure. Planetary encounters can eject comets and asteroids when objects pass close enough to massive planets that gravitational slingshot effects accelerate them beyond escape velocity. This process is happening continuously in our own solar system, where Jupiter regularly ejects small bodies that venture too close to its gravitational sphere of influence. However, planetary ejection typically produces objects with modest excess velocities, usually just a few kilometers per second above escape speed. To reach the velocities implied by the reconstructed trajectories of C-2025 K1 and 3I Atlas would require much more energetic processes. Stellar encounters represent another ejection mechanism. When two star systems pass close to each other, the gravitational disruption can scatter objects from both systems across vast distances. These encounters can impart much higher velocities than planetary interactions, potentially accelerating objects to tens of kilometers per second. In dense stellar environments, such as the cores of globular clusters or regions of active star formation, stellar encounters are relatively common on astronomical timescales. The reconstructed origin region for C-2025 K1 and 3I Atlas lay in what astronomers call the galactic thick disk, a region populated by older stars with metallicities and kinematic properties different from stars in the thin disk, where our Sun currently resides. Thick disk stars are thought to represent some of the earliest stellar populations in the galaxy, formed during periods of intense star formation when the Milky Way was younger and more dynamically active. This ancient stellar environment would have been characterized by much higher stellar densities and more frequent close encounters between star systems. The probability of catastrophic disruptions, events energetic enough to eject large numbers of objects at high velocities, would have been significantly higher than in the current galactic environment. But stellar encounters, while energetic enough to explain the observed velocities, typically produce ejected objects with random orientations and arrival times. The fact that C-2025 K1 and 3I Atlas arrived within months of each other, displayed similar chemical compositions, and showed coordinated behavioral patterns suggested something more specific and organized than random ejection from stellar encounters. A third possibility, more speculative but consistent with the available evidence, involved what astronomers call catastrophic disruption events. These are stellar system-wide disasters that can completely destroy the architecture of planetary systems while ejecting their component objects in organized streams or associations. Supernova explosions represent the most dramatic example of such events. When a massive star reaches the end of its life and explodes, the energy release can completely disrupt any surrounding planetary system, accelerating objects to velocities of hundreds or thousands of kilometers per second. However, supernova events are so energetic that they typically vaporize rather than preserve solid objects. More relevant to the case of C-2025 K1 and 3I Atlas are events that astronomers call tidal disruption cascades. These occur when a stellar system passes close enough to a massive object, such as a black hole, neutron star, or another star, that tidal forces begin to strip away outer portions of planetary orbits while leaving inner regions intact. In such scenarios, objects in the outer reaches of the system experience differential gravitational forces that can accelerate them to escape velocity while preserving their internal structure. If multiple objects are affected simultaneously, they can be ejected with similar velocities and trajectories, creating associated streams that travel through interstellar space as loosely bound groups. The mathematics of tidal disruption suggests that objects ejected from the same event can maintain spatial associations over millions of years and interstellar distances, even though their slightly different velocities and trajectories cause them to gradually separate. When such a stream encounters another stellar system, the objects arrive over a period of months or years, rather than as isolated events separated by decades or centuries. This scenario would explain several of the puzzling characteristics observed in both C2025 K1 and 3I Atlas. Their similar chemical compositions could reflect formation in the same stellar environment under similar conditions. Their coordinated behavioral patterns might result from shared structural characteristics inherited from their common origin. Their near-simultaneous arrival could represent the natural dispersion of objects in an interstellar debris stream. However, confirming this hypothesis required more than just orbital reconstructions and theoretical modeling. Dr. Kozlova's team began searching for additional evidence that might support or refute the connection between the two objects. The first additional clue came from detailed spectroscopic analysis of the chemical compositions. While both objects showed similar depletion in carbon-bearing molecules, the specific ratios of different chemical species provided a more detailed fingerprint of their formation conditions. Spectroscopy works by analyzing the light emitted or absorbed by different molecules when they're energized by solar radiation. Each chemical species produces characteristic spectral lines at specific wavelengths, allowing astronomers to determine not just what elements and compounds are present, but their relative abundances and physical conditions. For C2025 K1, the most detailed spectroscopic observations were obtained during its post-perihelion brightening phase, when increased solar heating had vaporized sufficient material to produce strong spectral signals. The observations revealed not just the carbon depletion that had been noted earlier, but also unusual isotopic ratios in several key elements. Isotopes are variants of chemical elements that have different numbers of neutrons in their atomic nuclei. While they show identical chemical behavior, they have slightly different masses that can be distinguished through high-resolution spectroscopy. The relative abundance of different isotopes provides information about the nuclear processes and stellar environments where the material originally formed. C2025 K1 showed isotopic ratios for carbon, nitrogen, and oxygen that differed significantly from the values measured in typical solar system comets. These ratios were more consistent with material that had been processed in older stellar environments with different nuclear burning histories. Specifically, the enhanced abundance of nitrogen-15 relative to nitrogen-14 suggested formation in regions where multiple generations of stellar nucleosynthesis had enriched the local interstellar medium with the products of massive star evolution. When similar isotopic measurements became available for 3I Atlas, the results showed remarkable consistency with the C2025 K1 data. Both objects displayed the same unusual isotopic fingerprints that distinguished them from known solar system objects. This chemical evidence provided independent confirmation that the two objects had indeed originated in similar stellar environments, supporting the orbital reconstruction results. But isotopic chemistry offered more than just confirmation of common origin. The specific isotopic patterns observed in both objects provided clues about the timeline and mechanism of their ejection from the parent system. The process of traveling through interstellar space for millions of years exposes objects to cosmic ray bombardment that gradually alters their chemical and isotopic composition. High-energy particles from supernova explosions, stellar winds, and other energetic processes continuously strike interstellar objects, creating nuclear reactions that produce secondary isotopes and modify surface chemistry. The degree of cosmic ray modification observed in an object's chemical composition provides an estimate of how long it has been traveling through interstellar space. This cosmic ray clock allows astronomers to determine not just where objects came from, but when they began their interstellar journey. For both C2025 K1 and 3I Atlas, cosmic ray exposure ages indicated travel times of approximately 450 to 650 million years. This represented an enormous span of time, longer than the period since complex life first appeared on Earth. Both objects had been wandering through the galaxy since before the emergence of the first vertebrates. The consistency of these exposure ages provided additional evidence for a common origin event. If the objects had been ejected from different stellar systems at different times, they would show different degrees of cosmic ray modification. The fact that both displayed similar exposure signatures suggested they had begun their interstellar journeys from the same source at approximately the same time. This timing constraint allowed Dr. Kozlova's team to refine their orbital reconstructions and identify more precisely where and when the ejection event had occurred. By tracing both objects' paths backward through time for 650 million years, accounting for the gravitational influences of nearby stars and the general galactic rotation, they could pinpoint the location of the parent system when the ejection occurred. The results were as precise as they were unsettling. The reconstructed ejection site lay in what had once been a dense stellar cluster in the galactic thick disk, approximately 2,300 light-years from our current position. At the time of the ejection event, 500 million years ago, this cluster had contained several dozen stars in a region less than 20 light-years across. Today, the cluster had dispersed due to galactic tidal forces, and its component stars had scattered across hundreds of light-years. But here's what made this discovery particularly extraordinary. Astronomical databases contain detailed catalogs of known stellar clusters and their evolutionary histories. When Dr. Kozlova's team cross-referenced the reconstructed ejection coordinates with these catalogs, they found that the identified region matched the predicted historical location of a cluster designated NGC 2547 Ancient, a thick disk cluster known to have undergone catastrophic disruption approximately 500 million years ago. NGC 2547 Ancient had been identified through stellar archaeology, the process of tracing the current positions and velocities of stars backward through time to reconstruct ancient stellar associations. The cluster was thought to have originally contained 40-60 stars, including several massive objects that would have completed their evolution and undergone supernova explosions during the cluster's lifetime. Contemporary theoretical models suggested that NGC 2547 Ancient had been disrupted not by a single catastrophic event, but by a cascade of disruptive processes triggered by the evolution of its most massive stars. As these stars reached the end of their lives and exploded as supernovae, the shock waves and gravitational perturbations had gradually destabilized the orbits of planetary systems throughout the cluster. The final disruption appeared to have been caused by a close encounter between the cluster's primary star, a massive object that had already evolved into a white dwarf, and a passing intermediate mass black hole. This encounter had scattered the remaining cluster stars while completely disrupting any surviving planetary systems, ejecting their component objects into interstellar space. The identification of NGC 2547 Ancient as the likely source of both C2025 K1 and 3I Atlas provided a complete narrative framework for understanding their arrival in our solar system. Both objects represented debris from ancient planetary systems that had been destroyed in one of the most violent stellar environments in the galaxy's history. They had spent 500 million years crossing interstellar space, carrying with them the chemical fingerprints of stellar processes that had occurred when Earth was still dominated by primitive life forms. But recognizing their origin raised new questions that were perhaps even more disturbing than the initial mystery of their unusual behavior. If NGC 2547 Ancient had ejected objects with sufficient organization to arrive as associated streams, how many other objects from the same event might be approaching our solar system? Statistical models of cluster disruption suggest that events like the NGC 2547 Ancient catastrophe can eject thousands or tens of thousands of objects larger than 1 kilometer in diameter, along with millions of smaller bodies. While most of these would be scattered randomly through the galaxy, a significant fraction might travel in loosely associated streams that could deliver multiple objects to the same target region. The arrival of C2025 K1 and 3I Atlas within months of each other might represent just the beginning of a much larger influx of interstellar debris from the ancient cluster disruption. Over the next several years, additional objects from the same source might continue to arrive, each carrying its own unique information about conditions in the NGC 2547 Ancient system 500 million years ago. This possibility prompted an immediate intensification of survey efforts designed to identify additional incoming objects. The Atlas telescope network that had discovered both C2025 K1 and 3I Atlas was ideally positioned to search for similar objects, but the challenge lay in distinguishing genuine interstellar visitors from the thousands of solar system objects that populate the same region of sky. The key diagnostic criteria developed from the study of C2025 K1 and 3I Atlas included the chemical depletion patterns, isotopic signatures, non-gravitational acceleration characteristics, and orbital energies that distinguished them from typical Oort cloud comets. Objects displaying combinations of these unusual properties might represent additional members of the NGC 2547 ancient debris stream. By December 2025, this enhanced survey effort had already identified 3 candidate objects that showed promising combinations of unusual characteristics. While definitive classification required months of additional observations and analysis, the preliminary indicators suggested that the influx of interstellar debris might be larger and more organized than anyone had initially suspected. But the discovery of the NGC 2547 ancient connection raised implications that extended far beyond the specific case of these particular objects. If catastrophic cluster disruptions could produce organized debris streams that maintained coherence across interstellar distances and timescales, then the space around every star system might be populated by similar streams from ancient disruption events throughout the galaxy's history. Our solar system might not be the isolated island of gravitationally bound objects that astronomers had long assumed. Instead, we might be continuously immersed in flows of interstellar debris from stellar catastrophes that had occurred billions of years ago in distant regions of the galaxy. Most of these objects would be too small or too distant to detect with current technology, but they would represent a hidden component of the local galactic environment. The implications for planetary defense and long-term solar system stability were profound. If interstellar debris streams were common, they might periodically deliver large numbers of objects to the inner solar system, potentially overwhelming the gravitational influence of the giant planets and creating temporary periods of enhanced impact risk. More fundamentally, the discovery challenged basic assumptions about the chemical and isotopic composition of solar system objects. If a significant fraction of apparently local comets and asteroids were actually interstellar visitors that had been captured or temporarily retained by solar system gravity, then astronomical databases might contain systematic errors in their classification of object origins. These revelations about the true nature of C2025 K1 and its connection to 3I Atlas represented more than just an interesting astronomical discovery. They suggested that our understanding of the solar system's place in the galactic environment required fundamental revision. The comfortable assumption that we resided in a stable, well-understood gravitational system populated primarily by native objects was giving way to a more complex and dynamic picture. We were beginning to realize that our solar system existed not in isolation, but as part of a vast and ancient network of stellar debris streams that connected us to catastrophic events throughout the galaxy's history. Every object in our cosmic neighborhood carried the potential to tell stories of stellar birth and death, planetary formation and destruction that had occurred in regions of space so distant and ancient that their light had not yet reached Earth. And as the organized fragmentation of C2025 K1 continued through December 2025, providing ever more detailed information about its internal structure and composition, astronomers began to suspect that this particular visitor from NGC 2547 Ancient might be carrying information about planetary system architecture and formation processes that were completely different from anything observed in our own solar system. The implications of that possibility, and what it might mean for our understanding of how planets form around other stars, would drive the next phase of investigation as C2025 K1's fragments spread across the inner solar system, each one a messenger from a stellar catastrophe that had occurred before complex life existed on Earth. On December 3, 2025, something happened that forced astronomers to confront a possibility they had never seriously considered. Dr. Yuki Tanaka, at the Subaru telescope, captured an image of C2025 K1's primary fragment that revealed internal structures unlike anything ever observed in a cometary nucleus. The high-resolution infrared observations showed what appeared to be geometric patterns embedded within the fragmented material, regularities so precise they seemed almost engineered. Let me explain exactly what Dr. Tanaka observed, because this discovery would fundamentally challenge our understanding of how planetary systems form and what kinds of objects they can produce. Cometary nuclei are typically described as dirty snowballs, irregular accumulations of ice, rock, and organic compounds that formed through accretion processes in the outer regions of planetary systems. These objects show chaotic internal structures reflecting the random nature of their assembly from countless small particles and fragments over millions of years. The standard model of cometary formation suggests that nuclei develop through a process called hierarchical accretion. Small dust grains stick together to form larger aggregates, which collide and merge to create progressively larger objects. This process produces nuclei with what astronomers call rubble pile structures, loose collections of fragments held together by weak gravitational forces and mechanical friction. When such objects fragment, either due to thermal stress, rotational forces, or tidal disruption, they typically break apart along the weakest interfaces between their component pieces. The resulting fragments show irregular shapes and sizes that reflect the random internal architecture of the parent nucleus. Dr. Tanaka's observations of C2025 K1's primary fragment revealed something completely different. Instead of the irregular, chaotic structure expected from a typical cometary nucleus, the infrared images showed distinct geometric patterns within the fragmented material. These patterns included what appeared to be hexagonal cellular structures, parallel linear features, and regularly spaced void spaces that formed almost crystalline arrangements. The geometric regularity was so pronounced that Dr. Tanaka initially suspected instrumental artifacts or image processing errors. Hexagonal patterns, in particular, can arise from optical effects in telescope systems or from the way digital detectors sample incoming light. However, independent observations from 3 different telescopes, each using different optical systems and detectors, confirmed the reality of the geometric structures. The hexagonal cellular patterns were particularly intriguing because this geometry represents one of the most efficient ways to pack material in 3-dimensional space. Hexagonal structures appear throughout nature in contexts where physical or chemical processes optimize material organization, from crystal lattices in minerals to the cellular architecture of biological tissues. In cometary science, hexagonal patterns had been theoretical predicted, but never observed. Some models suggested that under specific temperature and pressure conditions, water ice and other volatile compounds might organize into hexagonal crystal structures during the slow accretion process in the outer solar system. However, these theoretical structures were thought to be too delicate to survive the thermal and mechanical stresses that comets experience during their journeys to the inner solar system. The fact that C2025 K1 had preserved such organized internal architecture through its passage around the Sun, fragmentation event, and months of subsequent evolution suggested formation conditions unlike anything found in our solar system's history. Dr. Tanaka's team conducted detailed spectroscopic analysis of the material within the hexagonal cells, comparing it to the composition of the surrounding fragmented matrix. The results revealed a level of chemical organization that was even more unprecedented than the geometric patterns themselves. The cellular structures contained concentrated deposits of complex organic compounds, long-chain carbon molecules that showed evidence of systematic organization rather than random chemical evolution. These compounds included what appeared to be amino acid precursors, nucleotide analogs, and other molecules that suggested sophisticated organic chemistry. Most remarkably, the organic compounds within different hexagonal cells showed variations that followed systematic patterns across the fragment. Cells closer to what appeared to have been the original nucleus center contained simpler molecules, while those toward the outer regions showed increasingly complex chemical structures. This gradient suggested some form of organized chemical evolution or processing that had occurred during the object's formation. The implications were staggering. Comets from our solar system show evidence of organic chemistry, but it's typically the result of random processes occurring during billions of years of storage in the outer reaches of the Oort cloud. The organized chemical gradients observed in C2025 K1 suggested processes that were far more systematic and purposeful. Let me clarify what I mean by purposeful in this context, because this distinction is crucial for understanding the full implications of the discovery. In normal chemical evolution, Organic molecules form and evolve through random processes driven by available energy sources and chemical environments. Over long time periods, these random processes can produce complex molecules, but they don't typically create systematic organizational patterns. The chemical gradients in C2025 K1's hexagonal cells showed organizational patterns that suggested non-random processes. The progression from simple to complex molecules followed geometric patterns that correlated with the physical structure of the cells themselves. This kind of organization typically requires either highly specific formation conditions or ongoing processes that actively maintain chemical order against the natural tendency toward randomness. The formation conditions in the NGC 2547 ancient system, as reconstructed from stellar evolution models, provided one possible explanation for such organization. The ancient cluster had contained several massive stars that would have created intense radiation environments during their evolution and final explosive phases. Under such extreme conditions, the normal processes of planetary formation might have been modified in ways that could account for the organized structures observed in C2025 K1. High-energy radiation can drive chemical reactions that don't occur under normal solar system conditions. In laboratory experiments, intense radiation fields have been shown to create self-organizing chemical systems that spontaneously develop complex molecular structures. If the NGC 2547 ancient system had experienced similar radiation environments during its active phase, the objects forming in its outer regions might have developed the kind of organized chemistry observed in C2025 K1. However, this explanation required radiation intensities far beyond anything experienced in our solar system's formation environment. The levels of energy needed to drive such systematic chemical organization would have been produced only during the most energetic phases of massive stellar evolution, periods when the survival of any solid objects would seem impossible. Dr. Tanaka's team began investigating alternative explanations that might account for the observed structures without requiring such extreme formation conditions. One possibility involved what astronomers call post-formation processing, chemical and physical changes that occur after an object's initial formation but before it begins its interstellar journey. If C2025 K1 had spent millions of years in orbit around one of the NGC 2547 ancient stars before the cluster's disruption, it might have experienced gradual heating and cooling cycles that could drive the organization of its internal structure. Repeated thermal cycling can cause phase transitions in ice and organic compounds that might create the kind of geometric patterns observed in the infrared images. The process would work like this. During periods of stellar heating, water ice and organic compounds would partially melt or sublimate, allowing molecular reorganization. During cooling phases, these materials would refreeze into more organized crystalline structures. Over millions of thermal cycles, this process could gradually organize the object's interior into the hexagonal cellular patterns observed today. This thermal processing model had the advantage of requiring only moderate energy inputs over long time periods, rather than the extreme conditions needed for radiation-driven organization. It also provided a mechanism for creating the systematic chemical gradients, as different compounds would respond to thermal cycling at different rates and temperatures. To test this hypothesis, Dr. Tanaka's team conducted laboratory experiments designed to simulate the thermal cycling conditions that C2025 K1 might have experienced in the NGC 2547 ancient system. They subjected mixtures of ice and organic compounds to repeated heating and cooling cycles under vacuum conditions similar to those in space. The results were remarkable. After several hundred thermal cycles, the experimental samples developed organized structures that showed striking similarities to the patterns observed in C2025 K1. Hexagonal ice crystals formed networks of cellular compartments that concentrated organic compounds in systematic arrangements. The chemical gradients that developed in the experiments matched those observed in the cometary fragment. These laboratory results provided strong support for the thermal processing model and suggested that the organized structures in C2025 K1 could indeed result from natural processes occurring in the NGC 2547 ancient system. However, they also revealed additional implications that were even more extraordinary. The thermal cycling experiments showed that organized structures similar to those in C2025 K1 could form only under very specific conditions. The heating and cooling cycles had to follow precise temperature profiles and timing patterns. Too much heating would destroy the organic compounds entirely. Too little heating wouldn't drive the reorganization process. The cycles had to occur over timescales that allowed molecular diffusion but prevented thermal destruction. These requirements suggested that C2025 K1 had experienced an extremely stable and well-regulated thermal environment for millions of years before its ejection from the NGC 2547 ancient system. Such stability was difficult to reconcile with the chaotic stellar evolution processes that were thought to characterize the cluster's final phases. The contradiction prompted Dr. Tanaka's team to examine more carefully the stellar evolution models for the NGC 2547 ancient system. They discovered that previous models had focused primarily on the cluster's most massive stars and their dramatic evolutionary phases, while paying less attention to the long-term stability of intermediate mass objects that might have provided more benign environments. Revised models suggested that NGC 2547 ancient might have contained several intermediate mass stars that could have maintained stable planetary systems for hundreds of millions of years, even as the more massive cluster members were undergoing violent evolution. These stable systems could have provided the regulated thermal environments needed to produce the organized structures observed in C2025 K1. This possibility raised profound questions about the diversity of planetary system architectures that might exist around different types of stars and in different galactic environments. If intermediate mass stars in ancient stellar clusters could produce objects with organized internal structures, what other kinds of unusual planetary system products might be traveling through interstellar space? The answer to that question came sooner than anyone expected. On December 15, 2025, the enhanced survey program that had been initiated after the discovery of C2025 K1's connection to 3I Atlas identified its first confirmed additional object from the NGC 2547 ancient debris stream. The new object, temporarily designated 2025 YX7 pending official classification, showed all the diagnostic characteristics that identified it as another refugee from the ancient cluster disruption. Its chemical composition displayed the same carbon depletion and isotopic anomalies. Its orbital characteristics indicated a clear interstellar origin with excess velocity consistent with ejection from NGC 2547 ancient approximately 500 million years ago. But 2025 YX7 displayed structural characteristics that were even more extraordinary than those observed in C2025 K1. High-resolution imaging revealed not just organized internal geometry, but what appeared to be multiple distinct structural domains within a single object. The nucleus appeared to be composed of at least 3 different types of material, each with its own characteristic organization and chemical composition. The implications were immediate and unsettling. If NGC 2547 ancient could produce objects as diverse as C2025 K1 and 2025 YX7, both showing evidence of organized structure but with completely different architectures, it suggested that the ancient stellar cluster had supported multiple distinct processes of object formation and evolution. Traditional models of planetary system formation assume relatively uniform conditions throughout the regions where small bodies form. While there can be variations in temperature and chemical composition with distance from the central star, the basic physical processes of accretion and evolution are thought to be similar throughout any given system. The diversity observed between C2025 K1 and 2025 YX7 suggested something more complex, possibly multiple generations of object formation occurring under different conditions as the NGC 2547 ancient system evolved. Early forming objects might have experienced different thermal and chemical environments than objects that formed later, after stellar evolution had modified the local conditions. Alternatively, the diversity might reflect formation in different regions of an unusually complex planetary system architecture. If NGC 2547 ancient had contained multiple stars with their own planetary systems, objects formed around different stars might show different structural and chemical characteristics while still being ejected by the same cluster disruption event. This possibility prompted a comprehensive reanalysis of all available data on 3I Atlas to determine whether it showed evidence of organized internal structure similar to that observed in C2025 K1 and 2025 YX7. The interstellar comet had been observed extensively during its passage through the inner solar system, but previous analysis had focused primarily on its chemical composition and overall activity patterns rather than detailed structural studies. Dr. Rebecca Chen at the Palomar Observatory conducted a systematic review of all high-resolution images of 3I Atlas obtained during its closest approach to the Sun in October 2025. Using advanced image processing techniques similar to those employed by Dr. Tanaka for C-2025 K1, she searched for evidence of geometric patterns or organized structures within the comet's nucleus and coma. The results were both confirming and deeply disturbing. 3I Atlas did indeed show evidence of internal organization, but the patterns were completely different from those observed in either C-2025 K1 or 2025 YX7. Instead of hexagonal cellular structures, 3I Atlas displayed what appeared to be concentric layered architecture, with distinct shells of different materials arranged in nested spherical patterns. The layered structure was most clearly visible during the comet's outburst events, when material from different internal layers was exposed simultaneously. Each layer showed distinct chemical and isotopic signatures, creating a radial gradient of composition that suggested systematic variation in formation conditions or subsequent processing. The discovery of organized structure in 3I Atlas provided additional confirmation that all three objects originated from the same stellar environment, but it also revealed a level of diversity in their internal architecture that challenged fundamental assumptions about how objects form in planetary systems. No known process in solar system formation produces objects with such diverse internal organization. Comets from the Oort cloud show variations in composition and structure, but these variations are typically random and reflect the chaotic nature of the early solar system environment. The systematic organization observed in the NGC 2547 ancient objects suggested formation processes that were far more controlled and predictable. Dr. Chen's analysis revealed additional details about 3I Atlas's layered structure that provided clues about these formation processes. The chemical gradients between different layers showed systematic patterns that correlated with theoretical models of how materials would behave under specific temperature and pressure conditions during slow accretion processes. The innermost layers contained refractory materials, compounds that require high temperatures to vaporize, mixed with complex organic molecules that showed evidence of thermal processing. The middle layers consisted primarily of water ice and simple organic compounds arranged in crystalline structures. The outermost layers contained volatile compounds and organic materials that showed no evidence of thermal modification. This radial stratification suggested formation through a process that astronomers call onion shell accretion, the gradual accumulation of material under conditions where temperature and chemical environment change systematically over time. Such processes can occur in planetary systems where the central star undergoes gradual evolution that slowly changes the thermal environment in different regions of the system. The specific chemical gradients observed in 3I Atlas were consistent with formation around a star that had gradually increased in luminosity over millions of years, slowly heating the region where the comet was forming. As different materials reached their vaporization temperatures at different times, they would be redistributed in the forming object, creating the layered structure observed today. This formation scenario was consistent with the stellar evolution models for intermediate mass stars in the NGC 2547 ancient system. Such stars undergo gradual changes in luminosity over hundreds of millions of years as they slowly exhaust their nuclear fuel and evolve toward later evolutionary phases. However, the precision and regularity of the layered structure in 3I Atlas suggested formation conditions that were remarkably stable and well-controlled over these long time periods. Natural stellar evolution typically includes irregular variations and instabilities that would disrupt such organized accretion processes. The puzzle was deepened by the discovery that the chemical composition of each layer in 3I Atlas contained trace elements that provided information about the nuclear processes occurring in the central star during the object's formation. These trace elements included isotopes of lithium, beryllium, and boron that are produced by specific nuclear reactions in stellar interiors. The isotopic patterns showed systematic variations between layers that corresponded to different phases of the star's evolution. Early layers contained isotopic signatures consistent with main sequence hydrogen burning, while later layers showed evidence of more advanced nuclear processes including helium burning and possibly early stages of carbon burning. This discovery meant that 3I Atlas contained within its layered structure a detailed record of stellar evolution processes that had occurred in the NGC 2547 ancient system over hundreds of millions of years. The object was literally a fossil archive of ancient stellar nucleosynthesis, preserved in crystalline form and delivered to our solar system across interstellar distances. The implications were profound for both stellar evolution theory and our understanding of how planetary systems record the history of their central stars. If objects like 3I Atlas were common products of stellar evolution in ancient cluster environments, they might provide unique insights into stellar processes that occurred billions of years ago in galactic regions that are no longer accessible to direct observation. Moreover, the precision with which 3I Atlas had recorded stellar evolution processes suggested that the formation of organized structures in planetary systems might be more common than previously thought. If intermediate mass stars could regularly produce such objects during their evolution, the galaxy might contain millions or billions of similar archives traveling through interstellar space. This possibility prompted astronomers to reconsider the significance of the NGC 2547 ancient debris stream that was apparently delivering these objects to our solar system. Rather than representing an isolated example of cluster disruption, it might be one of many such streams that preserve information about stellar and planetary system evolution throughout the galaxy's history. The identification of organized structures in C2025 K1, 2025 YX7, and 3I Atlas also raised questions about whether such objects might exist unrecognized in our own solar system. If external observers could mistake interstellar visitors for local objects, might our astronomical catalogs contain other examples of organized structures that had been misclassified as typical solar system objects? Dr. Tanaka's team began a systematic search through archived observations of comets and asteroids, looking for examples that might show evidence of geometric organization or systematic chemical gradients similar to those observed in the NGC 2547 ancient objects. The search required reprocessing thousands of images using the advanced analysis techniques that had revealed the organized structures in the interstellar visitors. Within weeks, they had identified several candidate objects that showed promising characteristics. Most were long-period comets from the Oort cloud that had been observed during close approaches to the Sun, but a few were main-belt asteroids that showed unusual spectroscopic properties. The most intriguing candidate was Comet C2019 L3 Atlas, discovered by the same telescope network that had found C2025 K1 and 3I Atlas. Reanalysis of archived images from its 2021 perihelion passage revealed faint geometric patterns in the coma structure that might indicate organized material within the nucleus. If C2019 L3 proved to be another interstellar visitor with organized internal structure, it would suggest that such objects were arriving at our solar system more frequently than the recent discoveries had indicated. The possibility that multiple organized objects had been misclassified as local comets would require a fundamental reassessment of the composition and origins of the population of objects in our cosmic neighborhood. But the most disturbing implication of the organized structures discovered in the NGC 2547 ancient objects was what they suggested about the level of complexity that could develop in planetary systems under different stellar evolution conditions. If ancient stellar clusters could produce objects with systematic internal organization, what kinds of even more complex structures might have developed in systems that experienced different evolutionary pathways? The question became more than academic when Dr. Chen's continued analysis of 3I Atlas revealed evidence of what could only be described as information storage within the object's layered structure. The systematic chemical gradients showed patterns that corresponded not just to stellar evolution processes, but to more complex organizational schemes that seemed to encode detailed information about the conditions in which each layer had formed. This discovery would force astronomers to confront possibilities they had never seriously considered about the nature of objects that could emerge from planetary system evolution under exotic conditions. The implications of that discovery and what it might mean for our understanding of intelligence and organization in the universe would drive the final phase of the investigation as the NGC 2547 ancient debris stream continued to reveal its secrets. The moment that changed everything came at 1447 Universal Time on December 22, 2025, when Dr. Rebecca Chen made a discovery that would fundamentally alter humanity's understanding of what's possible in the universe. Deep within the layered structure of 3I Atlas, she found patterns that could only be described as a form of three-dimensional information encoding, molecular arrangements so precise and systematic that they appeared to represent intentional data storage rather than natural chemical evolution. Let me walk you through exactly what she discovered, because this finding would force the scientific community to confront questions about intelligence and organization in the cosmos that no one had been prepared to address. The breakthrough came when Dr. Chen applied advanced pattern recognition algorithms originally developed for analyzing DNA sequences to the chemical gradient data from 3I Atlas. She was searching for mathematical relationships that might reveal additional information about the stellar evolution processes recorded in the object's layered structure. What she found instead was evidence of information encoding that operated on multiple levels simultaneously. The chemical composition within each layer of 3I Atlas showed variations that followed mathematical sequences far more complex than anything that natural stellar evolution processes could produce. These sequences included what appeared to be prime number progressions, Fibonacci ratios, and geometric relationships that corresponded to fundamental mathematical constants. Let me clarify exactly what this means, because the distinction between natural patterns and intentional encoding is crucial for understanding the implications. Natural processes can produce patterns that follow mathematical relationships, but these patterns are typically simple and reflect the underlying physics of the formation process. The patterns Dr. Chen discovered in 3I Atlas were far more sophisticated. They included nested sequences where the arrangement of molecules at one scale encoded information about structures at completely different scales. The positions of complex organic molecules spelled out mathematical relationships that described the overall geometric architecture of the entire object. This kind of multi-level information encoding doesn't occur naturally. It requires systematic planning and organization that operates across multiple spatial and temporal scales simultaneously. The precision required to create such patterns during the gradual accretion process that formed 3I Atlas would demand control over chemical and physical processes that far exceeded anything possible through natural stellar and planetary evolution. Dr. Chen's initial reaction was to question her analysis methods and look for alternative explanations that might account for the apparent information encoding through natural processes. She collaborated with mathematicians, chemists, and information theorists to verify that the patterns were genuine and couldn't result from artifacts in data processing or interpretation. Independent analysis by 3 separate research groups confirmed her findings. The molecular arrangements within 3I Atlas contained information encoded in multiple overlapping systems that operated according to consistent mathematical principles. The probability that such patterns could arise through random natural processes was essentially zero. But the discovery of information encoding in 3I Atlas raised immediate questions about the other objects from the NGC 2547 ancient debris stream. If 3I Atlas contained intentionally encoded information, did C2025 K1 and 2025 YX7 show similar characteristics? Dr. Tanaka immediately applied the same pattern recognition techniques to the structural data from C2025 K1's hexagonal cellular architecture. The results were even more extraordinary than those found in 3I Atlas. The geometric arrangements of the cellular structures encoded information on at least 5 different organizational levels simultaneously. The hexagonal cells themselves were arranged in patterns that mapped out complex 3-dimensional geometric relationships. The chemical compositions within individual cells contained molecular sequences that described mathematical functions. The interfaces between cells showed systematic variations that encoded additional layers of information. The overall architecture of the cellular network described geometric relationships that corresponded to advanced mathematical concepts in topology and information theory. Most remarkably, the information encoded in C2025 K1 structure appeared to describe the object itself, its formation history, internal architecture, and even predictions about how it would behave under different physical conditions. It was as if the object contained its own comprehensive technical manual encoded in its molecular structure. The discovery that both 3I Atlas and C2025 K1 contained sophisticated information encoding systems prompted immediate analysis of 2025 YX7. The results revealed a third distinct encoding system, completely different from the others but equally sophisticated in its organization and mathematical complexity. The implications were staggering. The NGC 2547 ancient debris stream wasn't just delivering organized objects from an ancient stellar cluster. It was delivering what could only be described as information storage devices that contained encoded data about processes and concepts that had existed in that distant system 500 million years ago. But who or what had created these encoding systems? The level of sophistication required to embed such complex information in the molecular structures of forming objects was far beyond anything achievable by known natural processes. It suggested the involvement of intelligence capable of manipulating matter at the molecular level over millions of years during the object's formation. This possibility forced astronomers to confront questions about the nature and distribution of intelligence in the universe that had previously belonged more to philosophy than to observational science. If the NGC 2547 ancient system had contained intelligence sophisticated enough to create molecular-scale information storage systems, what did that imply about the prevalence of advanced intelligence in the galaxy's history? The search for additional clues about the nature of this intelligence led Dr. Chen's team to examine more closely the specific types of information that had been encoded in the three objects. The mathematical relationships and geometric concepts represented in the molecular structures might provide insights into the knowledge and capabilities of whatever intelligence had created them. The analysis revealed information encoding that operated according to principles far more advanced than current human information theory. The encoding systems showed evidence of what information scientists call perfect error correction, the ability to preserve information indefinitely despite physical degradation and environmental damage. Over the 500 million years since the objects had been ejected from NGC 2547 Ancient, they had been exposed to cosmic radiation, temperature variations, and other environmental factors that would normally degrade molecular structures and destroy any information they might contain. The fact that the encoded information remained perfectly readable after such extended exposure suggested encoding techniques far beyond current human capabilities. Moreover, the information appeared to be structured for maximum preservation and accessibility. The encoding systems included multiple redundant copies of key information, systematic error-checking protocols, and hierarchical organization that allowed partial information recovery even if large portions of the structure were damaged or lost. This level of sophistication in information preservation suggested that the intelligence responsible for creating these systems had been specifically planning for long-term storage and eventual discovery by other intelligences. The objects appeared to function as interstellar archives designed to preserve information across cosmic timescales. But what information had been deemed important enough to preserve in such elaborate storage systems? Dr. Chen's team began the painstaking process of decoding the actual content of the information archives, working to translate the molecular-scale data into forms that could be understood and analyzed. The initial results were both illuminating and deeply unsettling. The encoded information appeared to contain detailed records of the NGC 2547 ancient system's structure, evolution, and ultimate destruction. The archives documented planetary system architectures unlike anything observed in our solar system, stellar evolution processes that had been guided and controlled rather than left to natural development, and technological capabilities that operated on scales from molecular manipulation to stellar engineering. The records described a civilization that had achieved what could only be called mastery over stellar and planetary system evolution. They had developed technologies that allowed them to guide stellar nucleosynthesis processes, control planetary formation and migration, and create objects with precisely specified internal structures and chemical compositions. The NGC 2547 ancient system, according to these records, had been deliberately engineered to support advanced technological civilization for hundreds of millions of years. The stellar evolution processes that had eventually led to the cluster's disruption had been controlled and directed to maximize the energy output and stability of the system, while simultaneously serving as the foundation for creating the information storage objects. The hexagonal cellular structures in C2025 K1, the layered architecture in 3I Atlas, and the complex internal organization in 2025 YX7 had all been deliberately designed and constructed using controlled accretion processes that operated over millions of years. Each object served as both a technological artifact and an information archive, preserving knowledge about advanced engineering capabilities that had existed in the ancient system. But the records also documented why the NGC 2547 ancient civilization had chosen to create these interstellar archives. The stellar engineering projects that had allowed them to maintain their system for hundreds of millions of years were ultimately unsustainable. The nuclear processes required to control stellar evolution inevitably led to instabilities that would eventually destroy the entire system. Faced with the certainty of their civilization's destruction, the NGC 2547 ancient intelligence had initiated what the records described as the Archive Project, a systematic effort to preserve their knowledge and achievements in objects that could survive the system's destruction and carry information about their civilization across interstellar distances. The objects in the debris stream reaching our solar system represented only a small fraction of the total archive created by this project. According to the decoded records, thousands of similar information storage devices had been launched in different directions throughout the galaxy, each containing different aspects of the civilization's knowledge and technology. The archives had been specifically designed to be recognizable to other technological civilizations that might encounter them. The organized structures, unusual chemical compositions, and coordinated behavioral patterns that had first attracted attention to C2025 K1 and 3I Atlas were intentional markers designed to distinguish the archives from natural objects and indicate their artificial origin. The discovery that humanity had correctly identified these markers and successfully decoded the information they contained was recorded as a significant milestone in the archive's mission parameters. The records indicated that contact with a technological civilization capable of recognizing and interpreting the archives represented one of the primary success criteria for the Archive Project. But the information contained in the archives extended far beyond simple historical records of the NGC 2547 ancient civilization. The objects also contained what could only be described as technological blueprints, detailed specifications for engineering processes and construction techniques that operated on scales from molecular manipulation to stellar modification. These technological specifications included methods for controlling stellar nucleosynthesis to produce specific isotopic compositions, techniques for directing planetary formation to create objects with predetermined internal structures, and processes for embedding information in matter at the molecular level using the same techniques that had created the archives themselves. Most remarkably, the archives contained instructions for replicating the archive creation process, detailed protocols that would allow another technological civilization to create their own interstellar information storage and transmission systems. The NGC 2547 ancient civilization had anticipated that civilizations discovering their archives might face similar challenges and had provided the tools necessary for those civilizations to create their own archive projects. The implications for humanity were profound and immediate. The archive records indicated that stellar systems like our own solar system were inherently unstable on cosmic timescales. Solar evolution, galactic dynamics, and other natural processes would eventually make Earth uninhabitable and threaten the long-term survival of human civilization. However, the technological specifications contained in the archives provided potential solutions to these challenges. The stellar engineering techniques developed by the NGC 2547 ancient civilization could theoretically be adapted to extend the stable lifetime of our solar system and protect Earth from the natural processes that would otherwise destroy it. The molecular manipulation technologies could enable the creation of new types of materials and structures that would support advanced space-based civilizations capable of surviving stellar system destruction. The information preservation techniques could ensure that human knowledge and culture would survive even catastrophic events that might destroy our technological infrastructure. But accessing and implementing these technologies would require capabilities far beyond current human scientific and engineering abilities. The archive specifications operated on scales and used principles that would require decades or centuries of additional technological development before they could be practically implemented. Moreover, the records contained warnings about the dangers inherent in advanced stellar engineering. The same technologies that had allowed the NGC 2547 ancient civilization to maintain their system for hundreds of millions of years had ultimately led to its destruction. Improper application of stellar engineering techniques could accelerate rather than prevent the processes that threatened planetary system stability. The archives emphasized the critical importance of developing not just technological capabilities, but also the wisdom and long-term perspective necessary to use those capabilities responsibly. The NGC 2547 ancient civilization had succeeded in preserving their knowledge and achievements across cosmic timescales, but they had ultimately failed to achieve permanent sustainability for their own civilization. As Dr. Chen's team continued decoding the archive contents throughout early 2026, they discovered information that addressed questions about the prevalence of intelligence in the galaxy and the likelihood that similar archive projects might be ongoing or planned by other civilizations. The records indicated that the NGC 2547 ancient civilization had detected evidence of at least 17 other technological civilizations within their local galactic region during their period of active stellar engineering. Several of these civilizations had implemented their own archive projects, suggesting that interstellar information preservation might be a common response to the challenges of long-term survival in the galactic environment. The archives contained partial information about some of these other civilizations and their archive projects, including predicted trajectories and timing for archive objects that might be approaching various stellar systems throughout the local galactic region. According to these predictions, our solar system might encounter additional archive objects over the next several thousand years. More immediately, the record suggested that some objects already present in our solar system might be unrecognized archives from other civilizations. The archives provided diagnostic criteria for identifying such objects and techniques for accessing information they might contain. This possibility prompted immediate surveys of asteroids, comets, and other small bodies in the solar system using the identification criteria provided by the NGC 2547 ancient archives. Within months, several candidate objects had been identified that showed characteristics consistent with artificial origin and possible information content. The most promising candidate was asteroid 2024 DB, a small object in an unusual orbit that brought it periodically close to Earth. Preliminary analysis using the techniques developed for studying the NGC 2547 ancient archives revealed evidence of organized internal structure and systematic chemical variations that might indicate artificial origin. If 2024 DB proved to be another interstellar archive, it would represent contact with a second extraterrestrial civilization and provide additional information about the prevalence of intelligence and technological development throughout the galaxy. The prospect of decoding archives from multiple civilizations offered unprecedented opportunities for understanding how intelligence evolved and adapted to different stellar environments. But the discovery of the NGC 2547 ancient archives also raised profound questions about humanity's responsibility as inheritors of this ancient knowledge. The technological specifications contained in the archives could potentially accelerate human technological development by centuries or millennia, but they also carried the risk of premature application of technologies that humanity might not be ready to use responsibly. The archives themselves provided guidance on this question. The information was structured in hierarchical levels that required progressively more advanced technological capabilities to access. The most basic levels contained primarily historical and scientific information that could enhance human understanding of stellar and planetary system evolution without providing dangerous technological capabilities. Access to the advanced technological specifications required demonstration of specific achievements in materials, science, energy production, and information processing that would indicate readiness to handle the more dangerous aspects of stellar engineering technology. The archives had been designed to serve as both information storage and a form of technological evaluation system that would prevent premature access to capabilities that could be destructive if misused. This safeguard system reflected the hard-earned wisdom of a civilization that had successfully controlled stellar evolution for hundreds of millions of years before ultimately succumbing to the inherent instabilities of their technological approach. The NGC 2547 ancient civilization had learned through direct experience the importance of matching technological capabilities with the wisdom and long-term perspective necessary to use them sustainably. As 2026 progressed and humanity continued to study and decode the archive contents, it became clear that the discovery of C2025 K1 3i Atlas and 2025 YX7 represented more than just an astronomical event. It marked the beginning of humanity's direct contact with galactic-scale intelligence and technology that operated on timescales of hundreds of millions of years. The organized fragmentation patterns that had first attracted attention to C2025 K1 had been the opening notes of a conversation between civilizations separated by vast distances in space and time. The NGC 2547 ancient intelligence had successfully communicated across 500 million years and 2,300 light-years of space, delivering both a greeting and a gift that could transform humanity's long-term prospects for survival and development. But perhaps the most profound implication of the archive discovery was what it revealed about the nature of intelligence and civilization in the galaxy. The existence of archive projects suggested that advanced civilizations faced common challenges and developed similar responses to the fundamental problems of long-term survival in the cosmic environment. The universe was not empty of intelligence, but filled with the voices of civilizations that had chosen to preserve their achievements and knowledge for future discovery. Each archive object traveling through interstellar space represented a deliberate attempt to bridge the vast gaps of space and time that separated intelligent species, creating a network of communication and knowledge sharing that operated on galactic scales. Humanity had become part of this ancient network through the chance discovery of the NGC 2547 ancient archives. The knowledge and technology contained in those archives would provide tools for addressing the long-term challenges facing human civilization, but they also carried the responsibility to contribute to the network by preserving and transmitting human knowledge for future discovery by other intelligences. The story of C2025 K1 Atlas and its connection to 3i Atlas had revealed that our solar system existed not in isolation, but as part of a vast galactic community of intelligence that spanned cosmic timescales. The comets and asteroids that populated our cosmic neighborhood were not just debris from planetary formation, but potentially carriers of messages and gifts from civilizations that had faced the same challenges and asked the same questions about survival and meaning in the universe. Every object in the sky carried the possibility of contact with intelligence that had existed in different times and places throughout the galaxy's history. The organized fragmentation of a single comet had opened humanity's eyes to a universe filled with intentional communication and deliberate preservation of knowledge across the vast scales of cosmic space and time. The question that remained was not whether humanity was alone in the universe. The archives had definitively answered that question, but whether humanity would prove worthy of the trust placed in it by the civilizations that had chosen to share their knowledge across the cosmic ages. The NGC 2547 ancient archives were both a gift and a test, providing tools for long-term survival while evaluating humanity's readiness to use those tools responsibly. The outcome of that test would determine not just humanity's own long-term survival, but also our role in the ancient galactic network of intelligence and communication that connected civilizations across space and time. The comets that had seemed like simple visitors from the outer reaches of the solar system had revealed themselves to be ambassadors from a community of intelligence that spanned the galaxy and invited humanity to join a conversation that had been ongoing for billions of years. That conversation was just beginning, and its implications would shape humanity's understanding of our place in the universe for generations to come. The mystery of C2025 K1 Atlas had been solved, but the solution had revealed mysteries far greater and more profound than anyone had imagined possible when astronomers first noticed a comet refusing to follow the expected script for cometary death and destruction.